Moving forward in Chapter 2, we now want to talk about atomic properties. We know that atoms are made up of subatomic particles, and really the distinctions between different types of atoms all is going to come from the numbers of those different subatomic particles. And so the different atoms are defined by different properties, and so atomic properties are all going to be determined by the relative numbers of subatomic particles. How many electrons, how many protons, and how many neutrons. We know that each of those has their own unique properties. And the two that we really are going to care about are going to be, we know that distinguish things are charge, and then we're also going to say what the relative mass. Okay, so the charge that electrons are negative, protons are positive, and neutrons are 0. And then when we talk about relative mass, we could say that the proton and the neutron are about 1, right? They're about the same, and then electrons are going to be about 0. Okay, so when we say that by about 0, it doesn't mean that electrons actually have 0 mass. It's just a really, really low mass relative to protons and neutrons. So if you care about what the mass of an atom is, you really only need to know how many protons and neutrons you have in the atom. The first property of atoms that we're going to talk about then is atomic number. And this corresponds to just the number of protons in an atom. Okay, so all atoms of a given element have the same atomic number, and each different atomic number corresponds to a unique element. Functionally, what this means is that the number of protons, this atomic number, determines the name of the element. Okay, so when we say oxygen, oxygen's a type of element, we know that corresponds to a type of atom. Oxygen atoms are all of the atoms that have 8 protons in their nucleus. Okay, and so conversely, any atom that has 8 protons in it, we call that oxygen. So copper is 29, uranium is 92, whatever sort of number. So different types of elements are based around different numbers of protons in the nucleus. Okay, whatever the number of protons, that gives you the name of the atom. So atomic number is functionally the same thing as name. This number of protons in the atom determines the identity of the atom itself. While we could just talk about atomic number 6, atomic number 80, whatever we want, we also have atoms and elements have names. Okay, so oxygen, sulfur, molybdenum, whatever. But those names can be long. So generally we're going to use what are called chemical symbols, which is just going to be shorthand for the elements. And these are going to be 1 or 2 letters long. Some of these our symbols are related to the name. Hydrogen is H, oxygen is O. There are only a small handful of 1-letter chemical symbols, but importantly, one thing to note, it's always a capital letter. So hydrogen is always capital H, not lowercase h. Most elements have 2-letter symbols. The first letter is always capitalized, second letter is always lowercase. A lot of times it's just the first 2 letters of the word, so neon, N-E, aluminum, A-L. Things work so far, so good. Sometimes you can't use the second letter because chromium and chlorine are both CH. So chromium is Cr, chlorine is Cl. You just use that next letter. And then there are some that have the symbol has nothing to do with the name of the element in English. So sodium is Na, iron is Fe. Oftentimes these ones that don't make a ton of sense based off the word is based around the name of the element in a different language. Primarily they're Latin or Greek. There's a couple other languages that pop up in there in the periodic table though. One of the things to note, you do not need to memorize chemical symbols. You will always be able, you'll see this is a graphic of the periodic table. We'll talk a little bit more about that later on. But you will always have access to the periodic table where you can relate atomic number, name, and symbol. You don't need to memorize those things. But you do need to know that you can look them up on the periodic table and be able to use a periodic table. So I would expect you to use a periodic table when you're looking these things up. You'll just passively learn that oxygen is out because we use it a lot, but you don't need to memorize that. You just kind of passively will pick it up. And I want to reference again, the format matters. First letter always capitalized, second letter is always lowercase. When we see this CR, when we see it out of context, we want to remember that those two are together. Those two letters are together. That is one atom. When we say CR, we mean chromium, not a C and an R. Participation 6-4, question 1. What are the names of the elements with the following atomic numbers? A 6, B 24, C 50, and D 100. This is the first question on participation 6-4, due Thursday, June 4th at 11:59 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, what are the names of the elements with the following atomic numbers? It's 6, 24, 50, and 100. As a reminder, there's an additional resources folder in the module. If you go to the bottom of the module, you might find there's a periodic table in there that you can hopefully high resolution that is useful in answering this question. Okay, so the next property we want to talk about is then the charge of the atom. And so the total charge of the atom is based on the number of charged particles in that atom. So neutrons have no charge. Okay, they're neutral, so it doesn't matter how many neutrons are in an atom as far as determining the overall charge of that atom. All that matters is protons and electrons. If you want to have a neutral atom overall, you would have to have the same number of protons and electrons. So each proton is +1, each electron is -1, and so you would then have that possibility. Those need to be perfectly the same number to balance each other out to get you a neutral atom. So you could ask a question like, how many electrons are in a neutral nitrogen atom? Okay, and so we could look at this and we could think, well, we know atomic number is 7 because it's called nitrogen. So when we see that the name is nitrogen, that means the atomic number is 7. You could look that up, and you know there are 7 protons. Next, because it is neutral, you know that the number of electrons has to be the same as the number of protons, meaning there are 7 electrons in a neutral nitrogen atom. So this little kind of example, this little process right here is starting to get at what we want to be able to do with all these ideas about properties of atoms. When we say neutral nitrogen atom, you're conveying information. And you're conveying explicit information about how many protons and how many electrons are in that atom based on those properties, namely charge, neutral, and name, nitrogen. And so we're going to talk about all these different properties, and we want to be able to kind of put them all together with what those different kind of properties are, what they inform about the properties of these different atoms. And, kind of what's in the atom, what the subatomic particle picture is, all that kind of stuff. There's only so many properties here, but there's a lot of ways that all of these different ideas are all related to each other. We want to get comfortable working through all of those relationships. So atoms are not always neutral. They can change their overall charge, and it's based around losing or gaining electrons. Protons are positively charged, so if you change the number of protons, but that doesn't really happen because they're locked inside the nucleus in the middle of the atom. Electrons are moving around freely, independent of each other, and they're on the outside of the atom. So atoms can either gain or lose electrons. That number can change, and you create what's called an ion. So ions are just charged atoms, and they can be either positive or negative. So cations are positive and anions are negative. So we do want to remember that. One of the ways that I remember that from going all the way back to when I was in high school is that if you have cat, the T in cations looks like a plus sign. So it's a plus sign, so it's got positive charge on cations. Cat in general as a prefix means positive. An as a prefix means like negation in the sense of like not usually, but also negative charge in this case. The one thing that is confusing, that potentially can be confusing when we think about cations as positive charge, that comes from losing electrons because electrons are negative. Right, so if you say lose in the case of this cation, this sodium cation, you lose an electron, right? You've lost a negative charge, and the overall charge becomes positive because you can think you're subtracting a negative, right? You're subtracting the negative charge of that electron, making the charge that's left over on the atom become positive. So when we talk about ions, we can put that information onto our chemical symbol. And we add it on to the chemical symbol as a prefix, or as a subscript, sorry, after the symbol. Okay, so, and we'll note that we also, when we put the charge, the notation is we put the sign after the number. So for example, for an oxygen anion, so if we want to kind of parse this out, oxygen, it's called oxygen. So we have that with the O, right? And then the anion is represented by the fact that there's a negative and a charge of -2. So we put the 2 in front of the negative sign when we're denoting the charge in the symbol. Should be noted that when we're talking about charge, like functionally, if you were to ask what is the charge on this, you would still say -2. But when you're writing out the ion, you put the negative sign afterwards, or the positive sign, right? In the case if you have a cation. And so oxygen anion with a charge of -2 would be this O2 with the negative sign, calcium 2+. And you'll note I have how the language here. So I'll try to be, good, call them oxygen, the -2 oxygens. But a lot of time functionally when we're speaking, you would just say O2- or oxygen 2-. So this would be the actual word. So when I say O2-, or if you hear someone, or when you're talking about, or you read about these things, that's how you kind of say that, or the kind of common language that we use. Calcium 2+, along those lines. You're really just kind of literally reading out the symbols in the order that they show up. For our positives and negatives, for things that are plus or -1, we don't include the number. This is kind of an idea that we're going to see come up again, that chemists are pretty lazy when it comes to notation. If there's a 1 that could be written there, we generally just drop it. So instead of saying lithium 1+, we would just say lithium plus. And how you can kind of think about this idea is similar to, this is similar to like in algebra, where if you have just say x, you don't write 1x, but if you have 2, you write the 2x, or 3x, those sorts of ideas. But you don't write a 1 in front of x, you don't write 1x, you just call it x. So similarly, we just call this plus, whereas up here it was 2+, because there are 2 of those pluses, which really corresponds to losing 2 electrons. Okay. So with those definitions, we now want to move on to working through some ideas that we talked about previously of understanding the properties, how these properties are going to inform our subatomic particles. So how many electrons are in one atom of Ca2+? Okay, so we looked at, we have these notations, we have these things, but again, we're going to want to know, what do we want? I want a number of electrons. I want information about the number of subatomic particles in this nucleus. And we want to think about, well, what information do we have? We have to have other information about this atom. And explicitly, we're told it's calcium 2+. So one of the things that's in there is the name calcium. Once we have a symbol or we have a name, we know that that corresponds to number of protons. That will always give us that information. So it's calcium. We know that atomic number is then going to be 20. You can look that up on the periodic table, meaning that you have 20 protons in a calcium atom. Any calcium atom, doesn't matter what the charge is, always has 20 protons. The other piece of information is the charge on the ion. Okay? And we know that the charge on the ion is always equal to the number of protons minus the number of electrons. We know that neutrons doesn't matter because neutrons are neutrally charged. What matters is the number of protons and the number of electrons. So we can know that the total charge is the +2 right here. So that goes right there. Number of protons we figured out based on calcium. We can plug that right in there. So this becomes an algebra problem to figure out what the number of electrons is. So we can rearrange, we can do our math, move electrons to the other side, move the 2 over. We get that it would be 20 minus 2, which tells us that there are 18 electrons in one atom of calcium 2+. You'll note no information about neutrons. We have no idea. When you say calcium 2+, you got no clue how many neutrons are in that because the neutrons aren't charged. So the neutrons aren't affecting that it's called calcium, and they aren't affecting the charge. So those two pieces of information, name and charge, can't give you anything about neutrons, but they can give you information. You can figure out electrons and protons. The final property for atoms that we're going to talk about is mass. And namely, we generally refer or talk about mass using what's called the mass number. It is important to note this is a little bit different than actual mass. This is a counting measurement. It's going to be close to the actual mass, like in atomic mass units, but mass number is just a count of the number of protons and neutrons in a nucleus. So this is an entirely nuclear property. It doesn't depend on the electrons at all, because again, they have relatively no mass. So again, this is only looking at protons and neutrons. And so again, if we had something, a given atom contains 6 protons, 6 electrons, and 7 neutrons, what is the mass number of the atom? When we're talking about mass number, all that we care about is protons and neutrons. Okay, so if I want to know the mass number, it's just protons and neutrons, and I just add them together. So the mass number in this atom is 13. There's no subtraction, no addition, no subtraction, anything like that, just protons plus neutrons. In charge, you need to account for the negative on the electrons, but not for mass number. With mass defined, we can now talk about what are called isotopes. So these would be atoms with the same number of protons, but different number of neutrons. So if we think about why that's important or why that's relevant, equal numbers of protons means that those are the same type of atom. They'd have the same name, but different neutrons means they have different masses. So isotopes are atoms with the same name, same number of protons. So for example, carbon, right? They'd have a name, but different number of neutrons. So those are carbon atoms with different properties. Just like you could have, say, calcium atoms with different charges, ions that you form. Isotopes would be a situation where you're looking at different masses, but the same overall name. And so carbon, for example, is 6 protons, but you could have a carbon atom with, say, 6 neutrons or 7 neutrons or 8 neutrons. And because all of these atoms all still have 6 protons, we call them all carbon, but they do have different properties. And so we distinguish that they are all carbon, but with some slightly different properties by calling them isotopes. So these are isotopes of carbon. When we talk about these different isotopes, the reason why we still call them all carbon is that they all have the identical chemical properties, right? We said that chemical reactions are interactions between atoms, and they're mediated by those electrons. So because you have the same number of protons in the nucleus, a neutral atom has the same number of electrons on the outside of the atom. So all of these different carbon atoms, all these different carbon isotopes, all have the same chemical properties because they have the same number of electrons. The only difference between them is then in the mass. So we can still call them all carbon. They're just kind of slightly different flavors of carbon. And when we define them and we talk about their differences, we define them based off the element name followed by the mass number. So carbon 12, carbon 13, and carbon 14. Do you want to note this is a little tricky because we have a tendency to assume that this number 12 is the neutrons, but we'll note those are different. That is the overall mass number. So when you say carbon 14, that 14 corresponds to the sum of those two numbers. Because you know it's carbon, there's 6 protons, and you can figure out how many neutrons are in that particular isotope, but that 14 is the sum of those two numbers. It's not just the neutrons. So we put all this together in what we call the nuclear symbol. So the nuclear symbol describes an isotope. And as the name implies, it is nuclear symbol. It describes all of the things in the nucleus. So that's going to be protons and neutrons. It does not describe anything about electrons. So carbon 14 nuclear symbol is displayed in the middle there. You will note there are 3 pieces of information. First off is the element symbol. So carbon becomes capital C, which is the chemical symbol for carbon. We have number 6, which is the atomic number for carbon. That is the number of protons in the nucleus. And then the mass number, right? That's the integer, just number of protons plus number of neutrons. Sometimes this atomic number isn't included. So you'll see something like C14 without the 6. And the reason is because carbon, you figured out that carbon was C from looking at the periodic table. That's also where the number 6 comes from. So putting the C is equivalent to having that 6 be on the atomic number. But you will note that these numbers all, no matter what, when you're talking about this nuclear stuff, that all goes on the left side of the symbol before the letter. And you saw, remember the charge, when we did the charge previously, talking about ions, that went up here, right? So that, we can kind of think these different quadrants, these different locations where we put numbers relative to the symbol have particular meanings. And so we always do want to include them on those particular sides. All right, let's look at some examples now, because now that we want to kind of work through what these kind of isotope information. So what is the nuclear symbol for magnesium 24? I just want to start with what do we want? I'm looking for a nuclear symbol. So we're just asked what is a nuclear symbol. And so that nuclear symbol, now this is where we know we can read the problem and identify that it's a nuclear symbol. But now it's on you to know what that implies. So there's 3 parts to a nuclear symbol. We're going to need the chemical symbol, we're going to need the atomic number, and we're going to need the mass number. The information that we're given is the isotope name. And so if we look at it right now, what we're looking at is I have magnesium 24 as my isotope name. That magnesium 24 has 2 pieces of information inherently in there that we need to be able to parse out by knowing when we're given this format. Magnesium is the element name, and 24 is the mass number. So that's great. We already have the mass number, right? That was what we needed. We are good to go. So now it's just a matter of taking the element name and turning that into chemical symbol and atomic number. And in order to do that, we're going to want to look at the periodic table. We can find that magnesium is 12, atomic number 12. Its Mg is the symbol. And then 24 just comes over whole hog. At 24, we just keep that information right in there. And we get the Mg12 right there. So we can take that nuclear symbol from the isotope name, and this is that isotope name, magnesium-24, is trying to convey the exact same information as the nuclear symbol. So it's just kind of a matter of rearranging those, looking up that one extra piece of information, what the symbol is and what the atomic number is. But otherwise, it's the same information, just kind of repackaged. What we also want to be able to do then is translate from that sort of packaged information, nuclear symbols, into information of how many protons, how many electrons, and how many neutrons are in a neutral atom of 3115P. Okay. So we guys want to start with what do we want? And in this case, we can see that it is going to be these protons, electrons, and neutrons that we're after. This really is kind of what we really want to get to in the end, be able to take this very packaged information about atoms, this is all property information, and relate it back to this information on number of subatomic particles. So what information do we have? We just said it was all that information about neutral atom of 3115P. So that information with the P is a nuclear symbol, and there's a lot of information cooked into that nuclear symbol, right? We got a chemical symbol in there, that's the P. The atomic number is 15, and the mass number is 31. There's a lot of information in a nuclear symbol. There's another important piece of information that's kind of not so obvious, and that's the fact that it's a neutral atom. Remember that nuclear symbol only gives you information on the nucleus, protons and neutrons. So in order to figure out electrons, you need to know something about the charge of the atom, in this case, the fact that it's neutral. All right, so let's work our way through this, the information that we're given, and turn that into protons, electrons, and neutrons. So a good place to always start it's going to be that atomic number, because that is the most directly related to subatomic particles. Atomic number 15 means you have 15 protons. There's no math, no algebra. It is just, that's the information straight up. So if we want to take a look at electrons now, once we have protons, we know that they're related to electrons in that they're both charged. So we want to, once we have protons, we have that name information. If we want to know the charge information, electron information, we need to look at the charge. And in this case, we have a neutral atom. Neutral atoms, number of electrons is equal to the number of protons. Well, we had 15 protons, so I have 15 electrons in this atom as well. Okay, so we got protons, we got electrons, finally neutrons. And we know that the way that neutrons impart properties on the atom is in the through mass. And our mass number in this case is 31. Okay, we're told that, and we're given that information from the nuclear symbol, that 31 right there. And we know that that mass number is the number of neutrons plus the number of protons. Good thing we already figured out the number of protons was 15, so we can go ahead and plug that in. 31, that mass number, is going to be equal to neutrons plus 15. Okay? And so what that therefore means, do our algebra, neutrons is going to be 31 minus 15, which means there are 16 neutrons in this atom. So we can see this is kind of the overall idea. We want to be able to go between these two representations, subatomic particles, which is number of protons, electrons, and neutrons, and then the properties that they actually inform. Because we know what actually determines the properties of atoms, just the numbers of the subatomic particles. And so we want to be able to go back and forth between those representations. Another thing that this example demonstrates is why protons have that central role. Why do we say that protons give the name? Well, protons have a hand in both determining the charge, because they're +1, and in determining the mass, because they're big like neutrons. So that's why we use them in both of these instances to say, or they're kind of the main thing. Once you have protons, you have the name, and then, you know, electrons determine charge and neutrons determine mass, kind of filter into those different effects. Participation 6.4, question 2. How many protons, neutrons, and electrons are in an Hg atom with a charge of +2 and a mass number of 200? This is the second question on participation 6.4, due Thursday, June 4th at 11:59 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, how many protons, neutrons, and electrons are in an Hg atom with a charge of +2 and a mass number of 200? Once again, periodic table in the additional resources folder at the bottom of the module might be useful in answering this question. All right, so kind of want to sum up that, you know, these subatomic particles, we got 3 of them, and atomic properties are determined by the numbers of these different subatomic particles. Identity is protons, charge, protons and electrons, because neutrons are uncharged, and mass is protons and neutrons, because those electrons are small. So we do want to get comfortable with those ideas of what these 3 have. And again, we can see protons show up in all of them. They're kind of like the king particle. That's why they have the name. That's why they inform name, as opposed to electrons or neutrons, because those can also vary, ions and isotopes. Okay, 2 questions on participation 6.4 in this video. Plenty more videos to go, more questions to find. See you in the next one.